Now we're going to talk about something called Rolle's theorem. Rolle's theorem is a theorem that we're not going to do a lot with, but we are going to use it as a tool to get to something which is much more important, of more theoretical value, which is the mean value theorem. So first I'm going to state Rolle's theorem. It says this: if f of x is continuous on a closed interval AB, so the function is continuous on the closed interval, and f of x is differentiable Now what does that mean? Function is differentiable if the derivative exists. A function is differentiable on the open interval. So the function is continuous on the closed interval. It's differentiable on the open interval. Continuous means that the graph of the function has no holes, no vertical asymptotes, and no jumps. No holes, no jumps, no vertical asymptotes. The function is differentiable means there are no cusps. That the graph of the function does not come to a point. The next requirement is we must also have that f of a, the function value at the endpoint, and f of b, the function value at the other endpoint, must be equal. So what I'm going to do is draw several pictures, several graphs of functions that meet these requirements. We're going to see that all of these have something in common and see if we can figure what the conclusion of this theorem must be. So if we have a function is continuous on the closed interval AB, it's differentiable on the open interval from A to B, and the function values at the endpoints are equal. So this is one graph that meets this requirement. There's A, there's B. There's f of A, and f of b must be equal. Beyond that, we're allowed to have anything we like. So any curve that starts at this endpoint, ends at this endpoint, and is continuous and differentiable, we're allowed to be considering. So one possibility is this: the curve goes up and comes down. In fact, some people call this is the whatever goes up must go down property of mathematics. Rolle's theorem says, under these conditions, there must exist a point between A and B. There must exist a point C in the open interval A to B. There must exist a value of C somewhere in between A and B such that, and this is the requirement, this is the key requirement, the tangent line at that point must be horizontal. That is to say, if this is my point C, there exists a C such that the tangent line is horizontal, what we're saying is that the derivative at C must equal 0. Remember that if the derivative is equal to 0, that requires the tangent line has to be horizontal. Another possibility might look like this. Here's A, here's B. F of A, F of B must be equal, so F of A and F of B are the same height. Another possibility is the curve might go down, but then it must come back up because it's not allowed to have any holes, any jumps, or any vertical asymptotes. It's not allowed to have any cusps. We'll talk about that a little bit more later. But we can see in this case there must exist a C such that the derivative of the function evaluated at C must equal 0. That is to say, the tangent line at C is horizontal. And it looks like that's my value for C in that particular instance. other possibilities exist as well. Here's A, here's B. F of A and F of B are the same height. It could be this is the picture. Now, Rolle's theorem says that there must exist a C with the tangent line horizontal at that function value. Remember what that means in mathematics is there must exist at least one. In this case, there are three of them. There are 3 points at which the tangent line is horizontal. There is a C number 1, there is C number 2, and there is C number 3. So there may be more than one, but Rolle's theorem guarantees that there is at least one, maybe more, but at least one. Now, there are some other possibilities, and we'll draw some of those pictures here. Here's A, here's B. So here's f of A, which is equal to f of B. Suppose the function is constant. Now, some students are under the impression that this is where Rolle's theorem fails. It turns out this is where Rolle's theorem is true everywhere. Rolle's theorem says there must exist a point somewhere between A and B with a tangent line at that point horizontal. In this particular case, we're free to choose any point. At any point C, the tangent line at that point is itself the same as the function itself, and so it also is horizontal. So Rolle's theorem is true even in this scenario. In fact, any C that we choose has a horizontal tangent line, and so Rolle's theorem is true in that scenario as well. Notice that we're required to have the function to be differentiable. If we violate the differentiable requirement, if we allow the function to have a cusp, then Rolle's theorem might not work. Here's what that picture would look like. Here's A, here's B. F of A, F of B are the same height. But if we violate the assumption that the function must be differentiable, that might be the picture. So in this case, there is no point where the tangent line is horizontal, because at the cusp, the tangent line doesn't exist. There is no tangent line at the cusp. And so Rolle's theorem, that's the reason that we require the function must be differentiable. If you relax the differentiable requirement, then there is not necessarily a point where the tangent line is horizontal. Similarly, if we don't require the function to be continuous, suppose we have a vertical asymptote somewhere. Well, in this particular case, there is no point where the tangent line is horizontal because the asymptote causes the curve to not have a horizontal tangent. So in this particular case, there is no horizontal tangent, and so that's why that Rolle's theorem requires that the function has to be continuous. So, if you do have those requirements, here's A, here's B. F of A, F of B, the same height. If the function is continuous and differentiable, then there must exist at least one, maybe more, but at least one point where the tangent line evaluated there is horizontal. In this case, that might be C number 1, this might be C number 2. So that's Rolle's theorem, and we're going to use it as a tool to talk about something which is a little bit more important, which is called the mean value theorem.